begin. So today we're going to start talking about the next subtopic, which is refraction of waves. Okay, and so last week we talked about reflection, which is with an L. Okay, reflection. Okay, and so reflection is the changing of the direction of waves as it hits a reflector. Okay, but when it changes direction, okay, when the direction of propagation changes, everything else doesn't change. Okay, the velocity is the same, the frequency is the same, the wavelength is the same. The only thing that changes is the direction. And we assume that when it is reflected, okay, usually the assumption that we do is that that all the energy remains intact. It means all the reflection is perfect lah. Okay, there is no energy loss to the surroundings and etc. etc. Although in real life, actually, there is some loss of energy. Okay, but today we're going to look at the second phenomena, okay, which is the refraction of waves. Okay, the difference between the FLAC and the FRAC is so tiny that you need to make sure that you are mentioning the correct thing. Okay, and so we see the refraction of waves, okay, especially when we look at the waves that are coming towards the shore. Okay, that's an example of the refraction of waves. Look at the waves, okay, and compare their shape as when they are away from the shore and when they approach the shore. Okay, when they are away from the shore, they're kind of straight, but as they approach the shore, we find that wave refraction, okay, okay, causes the wave fronts, okay, to parallel the shape of the coastline. It means it begins to look more and more like the coastline, okay, as it is being refracted. Okay, so today we're going to talk about how refraction happens and how is it that the waves can take the shape of the shore. Okay, see, the shape of the shore is like this, the wave is like this. The shape of the shore is like this, the wave is like this. The shape of the shore is like this, the wave also is about the same. But over here, right in the open sea, it's a little bit, it's like a lot more straighter, straight. But as it gets nearer, it takes more and you can see the shape. Okay, you can see the shape more prominently and it will follow the shape of the tepi pantai lah. Okay, of the shore. Just give me 1 minute. Okay. All right. So we're going to talk about refraction first. I hope you have your module with you. So let's talk about when waves propagate from a deep water to the shallow water. Okay. So first of all, we want to compare the frequency of the water waves in the deep area and in the shallow area. Okay, and we find that in the deep area and in the shallow area, when refraction happens, the frequency remains the same. Okay, this is a ripple tank okay, so your ripple tank, and since the motor is moving, the frequency of the waves doesn't change. Okay, and this is the first thing that I need you to remember. Okay, remember when we talk about reflection, nothing changes except for the direction of propagation. But in refraction, okay, the only thing that remains the same is the frequency of the wave. Okay, that's the first thing. All right. Secondly, let's compare the speed in the deep area and in the shallow area. Okay, in the deep area and in the shallow area. And this one, if you stand by the seaside or at the sea, or the tepi pantai lah bahkan, okay, you can actually feel this one. As the waves come nearer and nearer to the shore, okay, the wave speed slows down. Okay, so the speed of the wave in the deep area is bigger than the speed of the wave in the shallow area. Okay, think of when you go to the, when you go to the seaside lah. Okay, the speed of the wave in the deeper parts, okay, of the sea is much faster. Okay, it's higher the wave speed compared to the shallow area. Okay, now thirdly, I mean, you take a look at this 1, 2, 3, 4, 5. So the speed is this, but this one, the speed baru ini kan, the speed is like this. Okay, compare the wavelengths. This is much easily seen in this diagram. Okay, you can obviously see that the wavelength of the deep area is bigger than the wavelength in the shallow area. Okay, so in terms of, remember the wave equation, F equals to F lambda. We find that F is the same. Okay, but when refraction happens, okay, if the speed increases, the wavelength also increase. If the speed decreases, the wavelength also decrease. And notice that both are always, the deep is always bigger than the shallow, but the frequency remains the same. Okay, a very important thing for us to remember when we're talking about refraction is that. Okay, so let's relate the depth of the water with the speed of the water waves. Okay, so we remember just now, okay, so this one is the wave speed is high, the wavelength is also big. This one, shallow area, the wave speed is low, the wavelength is also low. Okay, and remember how we write the words relate? Relate is the bigger the something, the bigger the something, kan? Okay, so this will be the bigger the depth. Okay, the bigger the depth, the bigger the speed of the water waves. Okay, big depth, big speed. Okay, or if you want to write it the other way also can lah. Okay, if your depth is small, kedalaman air kamu adalah kecil, cetek lah. Okay, air yang cetek, so your speed will be the smaller the speed as well. Okay, so it is directly proportional. Okay, now same thing, depth of the water to the wavelength. We find that if the wave speed increase, the wavelength also increase because it is in a deep area. So the same thing. The bigger the depth, the bigger the wavelength. Okay, or the other way lah, the smaller the depth, the smaller the wavelength lah. Okay, so it's directly proportional. And therefore, when we relate the speed of the water waves to the wavelength of the water waves, we will get the same thing lah. Okay, the bigger the speed, the bigger the wavelength. Okay, it is directly proportional to one another. Okay, so the first thing that we need to grasp, the first thing we need to understand when we're talking about refraction is that when refraction happens, the frequency is the only thing that remains the same. Whether it is in the deep area or the shallow area, the frequency is the same. The only two things that change is the depth, is the speed of the wave and the wavelength of the wave. Okay, where in the deep area, the speed will be much faster, the depth will be much bigger. Okay, and in a shallow area, the speed will be much smaller, the depth is also much, the wavelength is also much smaller because it's very shallow. Okay, so that is what happens when refraction is this one lah. But maybe you're still asking what on earth is refraction? Okay, so this one, refraction of waves is the change in direction of propagation of waves caused by the change in velocity of waves when the waves propagate from one medium to another. Okay, either one medium to another or as the wave propagates from mediums with different densities. Okay, but usually at this point, especially we are only doing chapter 5, we only talk about different mediums now. Okay, for example, in the case of the water wave just now, okay, we are talking, the different medium is the depth of the water. Okay, so deep water and shallow water, we will consider it two different mediums lah. Okay, dua bahan yang berlainan. But I would like to call it mediums with different densities lah. Okay, dia punya ketumpatan adalah berlainan sebab one is in deep water and one is in shallow water. Okay, that is for water wave. For light wave, okay, it will be the optical density of the medium. Okay, and this one we will talk about in chapter 6, not now lah. But I just want you to know that, okay, light will travel from water into, this is air, okay, and this is water. Okay, so look, when light travels from air to water or from water to air, okay, the optical density is different. Again, the word density. Okay, now if it is sound wave, Okay, then the speed of wave is influenced by the density of the air. Again, we see the words density. Okay, so cool air will have slower sound and slower speed. Okay, manakala warm air will have faster sound and faster speed. Okay, so we will also study this in a little while lah. Okay, but the idea is this: when refraction happens, okay, the direction of the wave is also changing. Okay, but not in the same way as reflection. Okay, if you remember reflection, reflection is if the light come here and then it will be totally reflected like this. Okay, there is a law of reflection lah. Okay, but or sorry, water wave lah, or this one lah, like echo, go there and then come back. But refraction of wave is you just change the direction, but it doesn't come back to you. Okay, and the change of direction happens because of the change of medium. If reflection, the change in direction happens because the waves hit a reflector. So it's two different things altogether. Okay, we need to know what is the difference between the two. Okay, so when we talk about refraction of waves, okay, we usually only refer to one formula, which is the general wave equation, okay, which is V equals to F lambda. But again, as I said before, the most important thing is that in the deep region or in the shallow region, or if let's say it is sound, if it is light, okay, like in this example, in the water and in the air, okay, or whether it's cool air or hot air, the frequency is always the same. Okay, and so because of that, we can derive this formula, which is the V1 over lambda 1 in the deep region is equals to the V2 over lambda 2 in the shallow region. Okay, there are some books that write this, V deep over lambda deep equals to V shallow over lambda shallow. But that is if it is only water wave. What if it is what if it is air and water, So that's why people generally write V1, V2 and lambda 1, lambda 2 lah. Okay, I think this is a little bit more fair. Okay, but again, the basis for this is because the frequency remains the same. If there is one thing that you really, really need to remember when we're talking about refraction of the waves, is that only the frequency is the same. Okay, in reflection, everything is the same except the direction. But in refraction, everything is not the same. Direction is not the same. Wavelength is not the same. Wave speed is not the same. Only the frequency is the same. Okay? So next, how does the direction of the water waves change when passing from the deep to the shallow water? Okay. So let's say this is a boundary. Yeah? Okay, this is the boundary we have. Okay, and there's a reason, there's a reason why the boundary is like saying it lah. Okay, so think of this boundary, think of this picture. Okay, the water moving from the deep and then to the shallow, right? But now I put the boundary over here. Okay, and let's say the wave is coming in this direction. Okay, now at the boundary, there is going to be this line now, which is perpendicular to the boundary, which we call a normal line. Okay, and so we find that when the wave is going from deep to shallow water, okay, it is going to refract towards the normal line. It means when it comes here, it's going to change direction, but the angle of theta 2 is smaller than the angle of theta 1. Okay, this angle theta 2 over here is smaller than the angle of theta 1 because it is refracting towards the normal line. It is getting closer and closer towards the normal line. Okay, I would like you to put a star over here and remember to write this lah. Okay, normal line, okay, is perpendicular, okay, to what is sempadan, to the to the what, sempadan, to the boundary lah. Okay, actually it's not the boundary. What is the word for sempadan? Sempadan lah. Oh, border. Sorry, border. That's even worse, I think. But never mind, fine. To the border lah. okay, to this sempadan. It's always 90 degrees. Okay, just like when we were drawing the reflection picture, remember last week I gave you the reflection picture to draw, and you first drew the reflector, and then the normal line is 90 degrees to the reflector. Okay, so we can call this boundary or the border over here as a refractor lah, if you want. But again, it is always 90 degrees. Okay, but we will find that when it's going from the deep water to the shallow water, the waves refract towards the normal line. It's getting closer. Okay, refract closer towards the normal line. But when it goes from the shallow to the deep, okay, again, this is the boundary over here. I'm going to draw this normal line over here. We find that this angle, okay, theta 1, and this angle, theta 2, okay, we find that it's going to refract away, okay, from the normal line. Okay, theta 2 is going to be bigger than theta 1. Okay, theta 2 is going to be bigger than theta 1, which is terbalik from this lah. Theta 2 is smaller than theta 1. Okay, so there is these two concept words that are very important here. Either it is reflecting towards the normal line or it is reflecting away from the normal line. Okay. All right, so let's talk about the characteristics. Let's give a slightly let's give a short summary lah. Okay, short summary to all this. Okay, again, we have the words angle of incidence and angle of refraction, okay, which we know here. So I'm going to call this theta 1 is the angle of incidence and theta 2 is the angle of refraction. Theta 1 is the angle of incidence, I, and theta 2 is the angle of refraction. Just like in reflection, angle of incidence is the angle before the phenomena. Okay, an angle of reflection, angle of refraction is the angle after the phenomena. Okay, so when water waves passes from the deep to the shallow water, okay, the angle of the incidence is bigger than the angle of the refraction. Okay, just like we saw here just now lah. R is smaller than I. Okay, or I is bigger than R lah. Either way is okay. Okay, but when water waves pass from shallow to deep water, which is this, okay, the I is going to be smaller than the R, which is this. Okay, the next important fact that you have to remember. Okay, which angle is bigger than which one? Secondly, the speed. Okay, this one we've already done now. When it goes from deep to shallow, the speed will decrease. The wavelength will decrease, but the frequency will remain unchanged. Okay, when it's going from shallow to deep water, it's going to go faster. So it's going to increase speed, it's going to increase wavelength, but the frequency will still remain the same. Very, very important thing is this. Okay, so again, as with learning everything that is new, okay, there's a lot of new terminology lah. Waves introduce us to a lot of new words that we need to get used to. Okay, so it will take us some time lah. Okay, don't worry, just make sure you understand where we're coming from. But the important thing is this lah. Okay, I would say that of all the points, this first point is the most important. Okay, is that when it moves from deep to shallow water, which angle is bigger than which one? Okay, incident angle is before refraction and refracted angle is after refraction. Okay, how you know which one is before and which is after? Take a look at the arrow lah, guys. Okay, this one also this one no need to tell you one actually, but I'll just tell you just in case any one of you are that blur lah. Okay, how you know which one is before, which is after? Because the angle, the wave comes from here, okay, to here. So obviously the arrow tells us which is the incident and which is the refracted angle. Okay, be very careful. All right, so the next thing we need to know is how to draw a diagram. Okay, just like reflection the other day, we have to learn how to draw a diagram. And so soon lah, okay, soon you will need to once again do the same thing as the drawing. So prepare A4 paper, a protractor, and a ruler, okay, and a few pens lah. Okay, but the first thing is we need to talk about the ripple tank experiment. Okay, so to show you how people actually do the drawing lah. Okay, so in a ripple tank experiment, which I hope that we can do when we go back to school, okay, is we have the ripple tank again. Okay, but over here we now have a perspex plate. Okay, we have a perspex plate which will make the water where, so the water that doesn't have the perspex plate will be the deep region, and the water with the perspex plate will be the shallow region. Okay, so we are expecting that when deep goes to shallow, we're expecting the wavelength to decrease, and we're expecting the wave speed to decrease. But again, remember that the frequency doesn't change because the frequency comes from the motor. Okay, this motor over here is the one that is determining the frequency. So if you don't change the frequency of the motor is going to vibrate at the same frequency. The frequency doesn't change. What changes is the depth. Okay, what changes is the wavelength. What changes is the wave speed. Okay, so take a look at this video. This video is pretty old, but it is a highly important. Yeah, I know it's pretty old, but it's still important nonetheless. Okay, so as you can see here, this is all deep lah. Okay, this part up here is all deep. But over here, they probably put a plate over here to make the water a lot shallower. And so you take a look at the wavelength. Okay, look at this wavelength. Remember the wavelength is from one bright to another bright, right? And then this wavelength, okay, is another one bright to another bright. So when you look at this picture, you should immediately know that, oh, okay, the one with the bigger wavelength is deep, and the one with the smaller wavelength is shallow. Okay, that's a very important thing that you need to remember lah. Okay, which side is deep, which side is shallow. This picture will automatically tell you why. Okay, notice also the wave speed. Okay, look at the wave speed. I'm going to rewind. I'm going to rewind this a little bit. Okay, look at the wave speed in the shallow and in the deep region. You notice that the deep one moves a lot faster. The wave speed is much faster than in the shallow region. And this one is slower, faster wave. Okay, so at this border over here, okay, is where refraction happens. Okay, where the wave speed, where the waves go from deep region to shallow region and change the wave speed, change the wavelength. Okay, although the frequency is still the same. Okay, so this is the same case. The wave is coming this way. Okay, the wave is coming this way. Okay, sorry, it's supposed to be straight. Okay, so the wave is coming this way, and look at this. This is the wavelength, and this is the wavelength. Obviously, by looking at the wavelength, you know that this is the deep region, and this is the shallow region. You know already. Okay, and we established just now that when it is going from deep to shallow, okay, it is going to, how is it going to refract? Is it going to refract away from the normal or towards the normal? Okay, we take a look back at this. As it's going from the deep to the shallow, it's it's going to refract towards the normal line. Oh no, sorry, it's going to refract towards the normal line. Okay, as it is moving from the deep to the shallow, it's going to refract towards the normal line. Sorry, let me see if I can find this one again. Oh, there. Okay. Okay, so obviously, okay, there is going to be some reflection, but let's not talk about this. But all I want to point out now is that, okay, if this is the boundary, okay, if this line here is the boundary, okay, we know that the normal line is 90 degrees to the boundary. Okay, so if I draw a 90-degree line, Okay, so this is the normal. So if I take, for example, this particular instance, we find that the wave speed is coming here, okay, and it's reflected here. Notice that this angle R and this angle I is, R is smaller than I because it's reflected towards the normal. Okay, deep to shallow. If you are ever in doubt lah, okay, if you are like, I don't know which one, how to know whether it's, deep to shallow, how do you know whether it is big, if the I is bigger than R or R is bigger than the I, right? Then you just remember, when it is deep, okay, when it is deep, the I is big. The angle is bigger in the deep lah. Everything is bigger in the deep. The wavelength is bigger than the deep. Wave speed is bigger in the deep, and the angle is also bigger in the deep. Okay, angle bigger means it is refracted away from the normal. Angle becomes smaller means it is refracted towards the normal. Okay, let me continue. Okay, same thing over here. Okay, same thing over here, except that this one is a little bit less prominent. Okay, we find that this is the boundary over here, and so the 90 degrees is over here. This is deep, this is shallow. Very obvious because the wavelength here is big. So it's going to be refracted. Macam mana? The same thing like just now lah. Okay. Now the other way, shallow to deep. Okay, so again, shallow is small wavelength, deep is big wavelength. Okay, and you notice that the shallow, the wave speed is much smaller, the deep, the wave speed is much bigger. Okay, the wave speed in the deeper region moves much faster compared to the slow one. Right? Okay, the same thing, okay, same thing as we saw just now. As the wave moves from a shallow to the deep region, it's going to be refracted away from the normal. Okay, because if you remember what I said just now, okay, in the deeper regions, everything is bigger. Okay, the wave speed is bigger, the wavelength is bigger, and the wave angle becomes bigger. Okay, angle from the normal. Okay, angle from the normal becomes bigger. So it's going to be refracted away from the normal. Okay, from deep to shallow, it's going to be refracted towards the normal. The angle is going to become smaller. Okay, continuing. Notice the wave speed also changes. Okay, same thing over here. This is the shallow, this is the deep. The wavelength is slightly bigger than the shallow. Okay, but again, we find that the wave refracts away from the normal. Okay, now notice that there's this square over here. There's a little bit of reflection happening over here lah. Okay, a little bit of reflection. Okay, this is total reflection, which is just reflection lah. So there is no hold on now. There's no refraction happening here. Okay, only reflection. There's no reflection happening. Everything is being reflected. Okay, because the thing over there is a reflector lah. So when you are drawing, later I will give you the instructions on how to draw. Okay, we are very specific lah. Okay, in this chapter we are really talking about deep, shallow, deep, shallow. We are very focused on just the drawing of the diagram for water waves. Okay, we're not so interested in the light waves yet because light waves we will learn in chapter 6. So we're very focused on water waves. So again, make sure that when you're drawing the deep region, you make the wavelength much bigger compared to the shallow region. Okay, make the wavelength smaller. Okay, now notice this, that this angle is at the same, this angle is really, the wave is coming at the same angle as the normal line. This is the boundary, right? Okay, and as I said just now, the normal line is 90 degrees to the boundary. And so since the water wave is coming at the same line as the boundary, as the normal line, okay, it's not going to change the direction. It's just going to faster, slower, faster again lah. Okay, it's not going to really change direction. It's just going to go straight because it is traveling on a normal line. But what usually we are more interested to see is that if the boundary is saying it like this. Okay, if the boundary is saying it, the first thing you need to do is to draw the normal line. How do you draw a normal line? You need to find something that is 90 degrees lah. Okay, so draw a perpendicular line, and then after that, make sure that you know that when it's going from deep to shallow, okay, the angle inside is going to become nearer towards the normal line. The angle is smaller. So this angle must be bigger than this angle. Okay, and not only that, when it is going from the shallow to the deep, okay, this is the boundary. So the normal line will be 90 degrees like this. Okay, so this is now the incident angle. So when it is refracted, okay, it's going to refract with this big R. Okay, guys, it's not going to refract this way. What is this? It's not going to refract this way. It has to travel on the other side. Okay, of the. It cannot be on the same. It cannot be on the same line. Okay, so be very careful. This is not right. Okay, they are kind of refract away from the normal. Okay, and so then after that, then you include the wavelengths. Okay, just to show. Okay, so how do I know which direction to draw the wavelength? Okay, notice that the wavelength, the wave lines, okay, and the direction of propagation of wave is always 90 degrees. Okay, if you look at this green color line, look at this green color line and look at the red color line. It's 90 degrees. No, it's really 90 degrees. To us, it doesn't look like 90 degrees because this line is saying it. Okay, but if you tilt your head a little bit, okay, you can actually see that this green and this red are actually 90 degrees to one another. So the single most important thing that you need to have, okay, in order to draw today's diagram correctly, is to have a protractor. Okay, and if you don't have a protractor, I would suggest that you find something that has a 90-degree angle, like a ruler. Okay, a ruler also can. A ruler is 90 degrees. This one, the angle of incidence and the angle of refraction, not so important. All I need to be able to see later is the difference in the angle. One must be bigger than the other. Okay, so if the angle in the shallow is small, I need just to be able to see that the angle is big in the deep region. Okay, because it's really refracting away from the normal. Okay, doesn't have to be rocket science lah. It doesn't have to be like so super exact lah. If you want to use protractor to be super exact, also can, no problem. Okay, but just agak-agak lah. One is bigger than the other. Okay, now same thing. Just now is go into the saying it and come out straight. But now we are going into the straight and then come out saying it. So what happens? When it's going from deep to shallow in the straight, it's going to travel in the same direction because the normal line and the direction of propagation is the same line. Okay, but as it goes to the deep, okay, since this is saying it now, we need to draw the normal line. Okay, so this is what we're going to see. The normal line is like this. And remember, shallow to deep. This angle, is it going to be bigger or smaller? This angle has to be smaller. So the refracted angle has to be much bigger. Okay, the refracted angle has to be much bigger and we will see something like this. Okay, then after that you draw your wavelengths. So pop, 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 pop. Okay, just follow this blue color line, draw the wavelength, and remember that shallow is smaller wavelength. Okay, and then after that the deep region, okay, is 90 degrees to this line. Okay, so you put your ruler here and then you draw 90-degree lines and you will get this, but with much bigger wavelengths. Okay, so I'm going to let you all go in a little while, okay, but what I need you to do is I need you to take out a piece of A4 paper, okay, and then get your pen and your paper and everything ready. Okay, I'm going to send you the instructions lah. Okay, macam last week lah, the same thing as last week. I'm going to send you the instructions on how to draw the refraction. Okay, how to draw the refraction punya diagram.